So far, we have been discussing Rolle's theorem. Rolle's theorem tells us that if you have some function where f of a equals f of b, so we're on some interval from a to b, and we're insisting that f of a is the same as f of b. It can be whatever you want in between, it can go up and come down, whatever, but it begins and ends at the same place. Then, as long as the function is nice, it's continuous and differentiable between a and b, then somewhere the derivative has to be 0. And sure enough, if you look at this example, you have here a couple places. Here the derivative is 0, here the derivative is 0, here it's 0. We just know there's at least one value, one place C. Here there are in fact several values where it's 0. Well, what we want to do in this video is we want to generalize Rolle's theorem to something called the mean value theorem. So we want to extend Rolle's theorem to the mean value theorem. So how do we do this? Well, what I want to do is I want to throw away the assumption that f of a is equal to f of b. So now I'm imagining a function where perhaps the value it starts at is not the same as the value it ends at this interval ab. Maybe f of a is down here, but f of b could be, say, all the way up there. Well, now if you have such a function, many things could look like. Let's just say the function looks something like this. If you have such a function, you say Rolle's theorem is no longer true. You're right, it is no longer true. It's no longer true that somewhere this derivative is equal to 0. Right? I mean, just look at this guy. This derivative is never equal to 0. It's always positive. It's always going up. Here it's just going up a little bit, but still going up. It's always positive. Rolle's theorem is false. But is there something else we can say that's true? Well, in the case of Rolle's theorem, you have that f of a and f of b were the same height. You had that they were the same height. And so you could think if you just draw a line from a to b, the slope there would be 0. And that comes out to be the same as the slope of the tangent line at this value c. Somewhere the slope was 0. In this case, if we connect a and b, the points at a and the point at b, your slope is no longer equal to 0. Rather, if we look at the slope of this guy, the slope will come out to be the difference of the y values, so this height will be whatever f of b is, minus this height, which is whatever f of a is, divided by the difference in the x values, b minus a. b minus a. And if a and b have different heights, if f of a is not equal to f of b, then this will not be 0. Okay, so you have a different slope. And so you shouldn't expect that somewhere the derivative to be 0. That only happened here when the slope between these 2 points, the secant line connecting those 2 points, is 0. Instead, here, you might ask, is there a point? Is there some point on this line where the derivative is the same as the slope of this secant line? So here it's much too big. If you pick a point like this, this has a slope much bigger than m. Or if you pick a point up here, it has a slope that's smaller than this line m. But there's some special point, maybe right around here, where if you look at the slope of this tangent line right here, f prime at this value c, f prime of c, in fact comes out to be the same as that slope m. So the new statement of the mean value theorem now, this extension of Rolle's theorem, is that the derivative is not going to be 0. Instead, it's going to be f of b minus f of a all over b minus a, which happens to be the slope from the points a to b. That's the mean value theorem. Now, secretly, Rolle's theorem is just a special case of the mean value theorem. When your f of a equals your f of b, this just comes out to be 0. But this is a much more general result. Here's another way you can think about this. If you look at this value, f of b minus f of a over b minus a, that is a description of your average rate of change. Average rate of change. Why is it your average? Because it looks at your starting value, it looks at your ending value, and looks at what is the average slope over it. What's the overall slope from this point to this point. Whereas your derivative is a measure of your instantaneous rate of change. The rate of change at some particular point. At some points it was higher than the average, at some points it was lower than the average, but there's some point where it's exactly the same. So let's think of an example to make this really concrete. Instead of just some abstract graph, let's imagine this was a graph where this x-axis is a time axis. It's measuring your time. And the y-axis is distance. So maybe this is measuring something like how fast the distance you've driven in your car over some amount of time. And if that's what you're measuring here, distance over time of you driving, then your derivative would be the change in distance. Your derivative, your slope, would represent your speed. This would represent your velocity. M would represent your average velocity. Whereas f prime, the derivative, would be your instantaneous velocity. And so what the mean value theorem is simply saying is that somewhere, at some point, your instantaneous velocity is equal to your average velocity. Think of it this way. Say you go on a road trip, and from the beginning to the end, you drive for 2 hours. You drive a total of 130 miles, so you're driving on average 65 miles per hour. Or for the non-American friends, that's what, like 100 kilometers per hour. Let's say you're driving on average 100 kilometers per hour. That's your average velocity. Well, while you were driving, there were probably moments in that trip where you may have been going faster than 100 kilometers. That's quite fast. Maybe this is reckless. Don't do this. Don't do this on the streets. But one could drive, and maybe at portions of that you were driving 110 or 115 or 120 kilometers per hour. Other portions of it, you were driving less than 100 kilometers per hour. You were driving, say, 80 or 60 or 40, when you slow down kilometers per hour. But the overall average was 100 kilometers per hour. That's your average velocity. What the mean value theorem tells us is that at some point, your instantaneous velocity must have obtained that average. And this should make sense. You can't always have been driving faster than 100 kilometers per hour, because if you're always going faster than 100 kilometers per hour, then your average would have been bigger than 100. And you couldn't have always been going under 100 kilometers per hour, because if you're going under 100 kilometers per hour all the time, your instantaneous velocity was always smaller than 100, then your average would also be smaller than 100. In order for your average to be 100, sometimes you're bigger, sometimes you're smaller, but then, by the intermediate value theorem, there must have been a moment where your instantaneous velocity actually equaled your average velocity. So again, this just follows from the intermediate value theorem. If it's a nice function, if it's differentiable, continuous differentiable, then at some point your instantaneous velocity, more generally your instantaneous rate of change, is equal to your average velocity, your average rate of change. That's what the mean value theorem is saying.